Hey, this is Steven from Legit Tech Tutorials and the Green Engineers, and welcome to my first episode of a new season. This is the DIY Metal Router number 2. I have a project that I was working on, and I thought that I would use a mill, but in actuality, I think a router is a better course of action for making this product. Basically, I'm building a shop inside of my garage because a local shop called the Shop.Build is looking a little like it's struggling, and I wanted to have my own machinery that I could use to mass manufacture very specific products to where I don't necessarily have to share, I guess you could say. So something that I could depend on and come home and just start them. And it's time to start investing in getting my own machinery if I want to do this for real, which I do. Manufacture these products for real. I need to start getting into either buying or making some of my own custom machinery to manufacture these products. Give me a second. I'm walking over here to let my cat out. Basically, the idea is that I want to be able to manufacture these machines to go inside of my garage on top of this shelf that is going to house all these machines and be able to manufacture these key products. This particular one is the shredder known as the Reclaimer, and it basically has, let me show you guys here. So this is the folder that's going to be in Fusion. And of course, as always, we're going to design everything in Fusion, as always. Shredder. So it has this this rotating section here. So if we look at the shredder assembly, it has this rotating section here. So how it was originally designed was it was designed to be pieced together using a water jet or a laser cutter or a plasma cutter. And then you have a separate shaft that goes through, and then you basically put the pieces on here like so. And so instead of that, what I decided to do is this shaft here. I decided to cut out of a solid piece of 3.5 inch round bar, basically. So you can see that the blades go right up to the top of this thing here. So basically, from blade tip to blade tip is 3.5 inches. So basically, have a fourth axis come in here, hold this, and a 3-axis come in here with a small cutter and cut this all out. And you can see that there's these pieces here which are highlighted, which are the spacers. These are what hold the gaps between these. So in actuality, this is just no longer going to be spacers. They're just going to be parts of the shaft. So now the shaft itself is not this hex bar. It's actually this circular piece here. So this is going to be basically solid, and solid means that when it comes off the machine, it's ready to go. You take it off and you could put it on to your machine. Every time I want to press the button on this machine, I want to get all the parts to make one shredder off at once. So I load all the material on, I press the button once. After that part comes off, it's ready to go. Everything is completed. So I just have to put it together. So I put this together, I put these pieces together. So I slide the shaft in, I press the bearings in to these top pieces, and I basically weld it shut on the sides here. So that is kind of the idea. So the reason why I'm thinking that normally on metal you would use a mill. Now I do want to build a mill, but I think that's just for various a CNC mill, but I think that's just for various parts and things like that. So I think normally I'm just going to stick with a metal router, and I'll show you why. So here's the tab that we're building stuff in here. So one of the big places that I go, there's a place that I go buy tools called Advanced Tool Supply in Santa Clara, and they have two main brands of they have multiple main brands, but the two main brands I buy, they have helical, melon. Melon's the cheap version. Then you have helical, which is slightly more expensive. And then you have Niagara. And then Niagara's the way more expensive version. So if you go here and you shop by cutter type, because obviously these use end mills. So I'm looking for browse by material, aluminum, and we want to do roughing. And everything that we're going to be doing is all adaptive, which you'll see later. So we're just going to go variable pitch, helix, triple flute. So basically they have an 1/8 inch, right? And if we go here, feeds and speeds, and we click on this guy, it'll download this document. And if we zoom in here, we'll notice that here for 1/8 inch, we have for 60. So, I looked up. These are actually this machine is going to mainly cut steel and cut some aluminum for some other parts. So let's look at some roughing for aluminum. For steel. So multi-flute corner range knuckle rougher. So let's look at 4-flute square variable pitch. So probably Niagara will probably be a better tool for this, or even some Ken Metal tools, which I would probably have to special order. Anyways, so if we look here, we have an 1/8 inch cutter, and it says here roughing we want 0.0012. So I'm going to go to this website. It's called Ken Metal. It's called Ken Metal Cutting Forces. So you just type Ken Metal Cutting Forces into Google. Why is it not going up? There we go. Ken Metal Cutting Forces, kenmetal.com resources, engineering calculators, turning calculators. It always comes up with turning calculators, but then you click on engineering calculators, end milling, force, torque, and power. So basically what we have is we're going to have the material is 1045 steel. 1045 steel. So we want the hardness of 1045 steel. And the hardness is in Rockwell B, which is 84, or Rockwell C. It'll convert it for us. So here we have Rockwell B, it's 84. So we're going to go here, Rockwell B, 84, 84. We want our units in inches. Okay, Brunel hardness 161. Effective cutting diameter, we're going to use inch, 0.125. Number of cutters, we have, not this one. We're looking at 4-flute. 4-flute is kind of tight for steel, but because we're doing adaptive, we'll have some room to clear. But it's going deep. It's going pretty deep down in there. It's going about 3/4 deep or something like that. It's going pretty deep, or almost 1 inch deep. So it's going, basically 8. What is that? 8 times? 8 times. It's going 8 times diameter. So here, let's look at this guy. So this is the, I got rid of the wrong one. Speeds and feeds. Standard feeds and feeds. Feeds and feeds. Okay, so this is the one we want here. So we're looking here, carbon steel, 1045 normal, low, medium carbon steel. No exotic alloys or anything like that. Or ASTM A36 might be another type that we use, which is just regular. I call it junk steel, but it's just structural steel, just regular low carbon structural steel. Okay, so if it's under 775 Rockwell B, this is above 75 Rockwell B. So we're at in between here. So we're at roughing is 0.009, but we're kind of close to slot. So I'm going to say we'll go slot. And also we want to be very gentle on these routers, and I'll show why later. So 0.007. So quarter feet per 2.007. And then it's saying that we have a 450 surface feet, and that's basically the speed that the cutter is traveling relative to the surface. Actual depth of cut, we'll do like a 1/16. Because the idea is that we're supposed to be running really, really fast. So 1/16 is still half diameter, which is quite a bit. So maybe we'll even go like 30, which is like a 1/4 diameter. 0.030. Machinability factor, so we're doing steels, carbon steels, but we're still doing very, very little width depth. So here, category tool wear factor. Sorry, my cat's crying here. Let me let her back in. Sorry about that. So tool wear factor, taking extremely light depths of cut. So we're gonna enter in a 1 here, and this is the machine efficiency. It's direct drive, so it's not very efficient. So it's about half efficiency. So let's go ahead and see what speeds it wants. So this is the main reason why I think a router is a good idea. So we see here spindle speed. It wants 13,751 RPM. So most, even like most Tormachs, I think the only one that gets up to here is the 440, which gets close, but that's a 10,000 RPM spindle. And yeah, so that's number 1. Number 2 is that you have to buy more expensive power heads or spindle heads in order to get up into these RPM ranges. Because again, a spindle is not really designed to go really, really fast. It's designed to be extremely rigid. So that's number 1. Number 2 is that a lot of these off-the-shelf machines, a lot of these off-the-shelf spindles for wood routers have actually stated that they have pretty good runout. So pretty low runout. So themselves. So if we go to AliExpress here. Oh, and then another thing that we want to look at here. So while we're here, let's go ahead and look at how much power. So down here, it'll tell us how much power. You see, it needs very little power because of how little we're going in with the 1/8" cutter into the material. Very little step over. So let's see if we do half diameter. 0.0625, 0.0625. Half diameter. Half diameter doubles because of this small feed rate, so 0.030. Oh, and then another thing that we want to look at is the cutting forces that are involved. So here are the cutting forces that are involved. We have 3.22 pounds of cutting force. So we have a decent cutting force here, but we need very little torque, but we still have 3 pounds pressing on the router itself. So let's see if we could simulate that 3 pounds. I have a small little, what's it called? I have a very precise scale right here. So let's see if we can't figure that out. So I don't have a pound mode, but I have an ounce mode. So ounce, we'll be able to transfer to pound, which there's 16 ounces in a pound. So let's see. It's like a cell phone, a modern day cell phone. What do we have? That's 5 ounces. So we're talking some considerable weight. Let's see, I have a LiPo over here. Because, like, you know, what exactly is 4 pounds, right? But here it says I only have 500 grams. So I'm not going to even be able to get to 4 pounds on this scale. Because that's only like 1.2 pounds. So yeah, it is a considerable amount of weight. It is a super high amount of weight to be putting on this, be putting on that spindle. So maybe, let's see if we could drop that a little bit. So I like to use this guide to kind of get a good idea of the forces involved. Again, everything in here, they say that it is, you know, obviously estimation. So what if we made it like a super low? There we go. So yeah, we just need to drop this down to get low. So what is this, like 1 pound? 1 pound. So that was 1 pound right there. It's a cell phone, a small camcorder, and a small LiPo battery. So altogether, I mean that's still a considerable amount of weight. So we might even go with the 15 thousandths. 15 thousandths. So yeah, maybe a little bit more than that. But we're moving at almost 40 inches a minute. So the deal is that we need something that spins really, really fast, moves at 40 inches per minute, and that uses these speeds, because these speeds are basically telling us at what speeds the harmonics aren't an issue. So what we need to do on this machine, which I have the Trello up, is that we need, obviously here, let's go ahead, let's look at some requirements. So we need to at least hold 1/8 inch, because these holes, these are 1/4 inch blades. So we need to hold, even if they were bigger, still probably wouldn't go higher than 1/8 inch. 1/8 inch cutter, call it. So it needs to be able to hold an 1/8 inch. It needs to be able to spin at least But the deal is that most motors in the middle of their RPM ranges where they make the most power. So the most power per RPM. So that's where they put down the most torque in RPM. I mean, and higher on the RPM. So, but they're less efficient there. So theoretically, we want something that has the highest torque at 14. So preferably if we have something that spins 28K, but most spin at 18K. So most max out at 18K. So here, what about horsepower? So here we're looking at horsepower, very negligible. So prefer run out over horsepower. So reason why, I don't know if you guys know a run out, anything about run out. But basically what run out is when something is spinning, it's how far does that spin deviate from the center. And basically what that's from is the quality of bearings and the quality of machining with all the components. So as this thing is spinning, if it moves a little bit off track, how much does it move off track? So for example, right here, the reason why that's a big deal is that because right here we're getting extremely close to almost rubbing the metal because we're taking such a small cut. We should probably even increase the cut because I'm getting a little scared about even rubbing here. So let's see what we have here. So basically, it's not doing anything. Anyways, it's not changing for whatever reason. Okay. So basically, as this thing's spinning, it's going to have this run out, and when you get really, really small tools, you need very, very small run out. Reason being is that, let's say this inch per tooth basically means that this is the distance that it takes into the cut at this depth. So let's say that we have this depth of cut down this way, and then this radial depth of cut. So this is like, let's say that there used to be a rectangle here. So it's going into the air this far this way and this far down to the edge of the cutter. Now, as it's progressing into that cut is this cut, which means that that you're cutting off 9 thousandths times this area, right? So that's what this is. It's a metal removal rate or a cross-sectional area chip. But remember also that it's not necessarily a square. It's scraping off circular because the cutter's circular. So it's like slicing it off as it spins around. So the lower this is, the smaller the chip is. Now, if you have a run out and you're thinking that if you were looking down this thing, down the barrel of this cutter, if you had like a 1 thou run out, it could go either 1 thou this way or 1 thou back this way. So basically what that means, or half and half. So let's say 5 thousandths this way, 5 tenths this way, 5 tenths this way. So basically what happens is if it goes 5 tenths this way, you're only taking 4 tenths into the cut. So basically what that means is that you're barely even cutting. You're only cutting, 4 thousandths, which is basically you're rubbing the material and you're going to have a lot of harmonics. Now, if you have 5 thousandths, it means that you're going 5 thousandths more into the cut. Let's say this way, you're going 5 thousandths more into the cut. Now you're taking 1.4 thousandths of an inch cut instead of your projected 0.009. So so let's say you have a 1 thousandths run out spindle. So now you're taking 1.9 into the cut, and you're not even cutting the other way. So there's so much run out that you're not even cutting going the opposite direction. If it's pushing back, which usually it just pushes back. So either pushes back or go forward. So that's why run out, especially on these small tools, is super, super important. So if these router bits work, then that would be preferable. So let's say, but the issue is finding one that has that low of run out, that is, there's a 30,000R. Ooh. But here's the deal. You want something that has a low run out, but as we noticed that we don't need really that much horsepower. I mean, this horsepower is tiny. But obviously this horsepower is relevant to where you are on the torque curve. And we're at the end, or towards the end. So we're going to have about 60% of its power rating. So if it says 750 watts, we're going to have about 60% of that. So we're going to have, 6 times that, 42 times this, that's 3. So 450 watts, which is fine. Oh, that didn't work. There we go. So we're going to look up actually 750 watt spindle, but let's see if it says what that run out is. Call it diameter 6mm 1/4 inch. Carbon brushes, but still 3,000 RPM. Wood here, aluminum body. But it's got a 1/4 inch collet, so I'd have to get a reduced neck cutters all the time. So this might be an option. And then this is like $100, about $36. So that's also something. So something like this would be like a power head. But we're looking at something like this. And also that's another thing, I would like to run off just wall power. So that's another thing that we'll look at. I wanted to just run off of wall power 110. So that will ease the ability of being able to install it in multiple locations. So let's look at just what we have with spindles. So here's a water-cooled spindle. This is a 2.2 kilowatts, so that's 3 horsepower. And so right down here you'll see, so run out here less than 0.005. So let's see. So let's leave that in the background, actually. So 0.005. So that's 2/10. So basically what that means is that we're either going to take we're going to either take a 1.1 thou cut, or we're going to take a 7 thou cut. So that's not that bad. So that's pretty good. And if we looked at some of these other head units, some of these power heads that we were looking at, you'll see that they also have way more run out. So that they'll have like 0.01 millimeters. So they'll have double this. So it's like 4/10 of run out, which is almost half of what we're supposed to have. So I was thinking maybe something to start out with. Oh, this is a 500 watt. These are 500 watt. 500 watt would even fly. And they're not water cooled, they're air cooled, and they're no VFDs. Because this one, I mean, it's pretty easy to just kind of set it. Because I'm going to be, again, this is for production. So if everything on the table is steel, then just run everything at the same speed and at the same chip load. So just set the speed and then on off switch. That's it. So nothing super crazy, right? I mean, this is going to be the first router I'm building ever. So, you know, I have a lot of experience with other routers and stuff, but this will be the first router I'm building. So, but see here, 0.01 to 0.03. So that's way too high. That's more than the power head. Yeah, it's like 1 point something. Because again, everything that's going to do is just going to wear out your cutters very, very quickly. So let's see if we could find something that is even down to that kind of spec that will be able to run that. And again, one of the biggest issues is because of how far this thing's extended out is one of the probably other reasons why. So here, repeat accuracy, which is basically run out 0.01 to 0.02. We just want tiny little call it. But you can see that this has a smaller shaft, so you want the one with the bigger shaft. It's fine. And then there's kind of the thing that we have to use to support. So let's see, what does this one say? So this one is 2 horsepower. 2 horsepower saying run out less than 0.005. So we might, this is kind of what we're looking at. Water cooled, again, we're not using, oh, what the heck? That was my mouse. Kind of not really using that much, so, you know, we want to watch our power usage here. And then, of course, they're water cooled, so that's not that great. Well, this is brushed. So maybe we could start out with something like that and just kind of see what happens. Because again, that's the issue. So 0.02 is pretty much our run out. It's pretty much our cut, our depth, our inch per tooth. So, But I'm wondering if a tiny little depth of cut and a tiny little load, how well it will fare. Well, we have these bigger guys. I think the only other way to get it is where it's like this, because then it uses this giant housing to basically take all the heat out of it. Ooh, see, this is not very good. 0.01's 4/10. Yeah, that's not gonna fly. If I was gonna spend that, let's buy this guy. So this is okay. So it's 2 horsepower kits, 286. So we're basically, or maybe we could look for something that is $200 for both. If we could find it somewhere, either 7 to half a kilowatt, 1 kilowatt. 1.5 for 250. This is an air cooled. So this one's 0.005. 0.005. So yeah, that's 2/10. It's better. Because again, I doubt we need to actually do that. I mean, pretty much all the friction is going to be from it, from basically the bearings in there. Yeah, $98 plus a VFD. Even though, again, I don't think that we're going to need nearly that much power. But look at how appealing this is here. Obviously, the runout's no bueno. And the reason being is that's why they could afford that. This guy is because it's DC. So that's how they could change the power on it. This is a 600 watt. It won't even hit our target RPM. So we're going to have to bump up the size to at least, ooh, there we go. Okay. Cone aperture to beat. What? Concentricity 0.0. Ooh. That's not very good. So yeah, something like that one, something like that one. Anyways, we're getting pretty close to the end, so I'll probably do, this isn't super important, so I'll probably look off video here to try to find something that will work, so we could kind of go from there. Alright, so this has been Steven from Legit Tech Tutorials and the Green Engineers. I thank you guys for watching this first video of the DIY Metal Router 2, design number 2, and I will see you guys next video. Thanks for watching. Take it easy. Peace.